Okay, we're going to pick up where we left off on the previous video. This is still section 5.2, discussing different probability formulas. We recently discussed what the probability of the complement to an event is. We said the union, which is an OR statement. This is a formula that is on the formula sheet. We will be discussing later the intersection, the AND, for two events, and then we did learn that at least the intersection of two events that are mutually exclusive, the probability of that would be 0. That's kind of what the definition of mutually exclusive means here. So let's go ahead and pick up where we left off here on example 8. It says we're going to let event A be a person has a cholesterol level of 240 milligrams per deciliter of blood or above. And event B is that a person has a cholesterol level between 200 and 239 milligrams per deciliter of blood. Okay. Apparently, anything between 200 and 239 is borderline high. Anything over 240 or 240 is high cholesterol. Okay. So according to the American Heart Association, the probability of event A is 0.16. The probability of event B is 0.29. Again, 240 or above is high cholesterol, and between 200 and 239 is borderline high. Question number 1 says, explain why events A and B are mutually exclusive. Okay, why these are mutually exclusive. Okay, so we're saying that the events A and B could not happen at the same time. Well, a person cannot have a cholesterol level that is greater than 240 milligrams per deciliter and a level that is also between 200 and 239 milligrams per deciliter. Okay, cannot be in those two categories at the same time. Okay, problem number 2 says, first of all, say in plain language what the event A or B is, and then we're supposed to find the probability of event A or B occurring. Okay, so what it means, event A or B, it means either someone has high cholesterol, okay, someone has high cholesterol, which is greater than 240 milligrams per deciliter, or it's between 200 and 239 milligrams per deciliter, which is considered borderline high. Now, we did learn in the previous video that OR also applies to both, but I'm not going to write that down because it's actually not possible that someone could be in both of these categories, but technically OR does mean both. Okay, now to calculate the probability, okay, if you remember the formula, and this is right above here in the box, and this is how it would look on the formula sheet, for the union of two events, an OR is each of those events' probabilities separately. So the probability of event A was 0.16, event B was 0.29, and then you subtract the intersection of those, which we had said in part 1 that events A and B are mutually exclusive. They cannot occur at the same time. That means their probability is a 0. Okay, so then we would say that the probability of event A or event B occurring is 0.45. Okay, number 3 says if C is the event that the person chosen has normal cholesterol, which would be a reading below 200 milligrams per deciliter, what is the probability of event C? Okay, so once again, this is talking about that their cholesterol level is under 200. Okay, well, let's look at what our answers. And you see this a lot on AP tests when there are free response questions and there are multiple parts. They tend to kind of build on each other. We even saw that with number 2 built a little bit on number 1 because we had already established in number 1 that the intersection of A and B was 0. had a 0 probability. And now in number 3, we're saying, well, what would be the probability that someone has a cholesterol level that is below 200? Well, we've calculated in step 2 the probability of them either having a cholesterol level that's between 200 and 239 or 240 or above. And so we could kind of use the complement rule here and subtract that probability from 1, and that would give us that there's a 55% chance there. Okay. All right, let's look at example 9. Here you're given information in what's called a two-way table, because we're given some variables across the top that represent the gender, male or female, and then we're given some variables across the left side here, which represents whether those individuals have their ears pierced or not. Okay. All right, so we're going to suppose that we were to choose a student from the class at random, and we're asked to find the probability that, and for part A, we're going to look for the probability that someone has pierced ears. Okay, so it looks like we've got 178 students total who were in this particular survey. Out of those 178, we want to know what are the chances of us randomly choosing someone who has pierced ears. Okay, so I'm interested in looking at this row right here where we said, yes, they have pierced ears. I'm going to glance all the way to the right and look at what that total is. There are 103 out of the 178 who have pierced ears. So that's a 57.87% chance. Okay. All right, now for part B, it says, again, these are all probabilities. We're going to find the probability that the student we choose is a male and has pierced ears. Now, if you look at the difference between parts B and C, they're just swapping this word out here. In part B, we want and then in part C, it will be an or. Okay, so let's go ahead and look at how to do the and. Okay, now we had said up above that we don't yet have a formula, for how to calculate the intersection. And that is true, but when you're given information like this in a two-way table, it is actually quite easy to find these and probabilities, okay? So I'm looking for, again, we're still talking about the full 178 students total here. Okay, but I want to look for where do the males and saying they have pierced ears intersect with each other. Okay, so I'm kind of looking down here at this column, at the male column, and then I'm looking over here at the yes, their ears are pierced column, and I see that those two things kind of collide right there at 19. Okay, so there are 19 males out of the 178 who have their ears pierced. So that is going to be my numerator here. Okay, and it is fine to leave your answers as fractions, or you could type it in and express it as a percentage. Okay, now let's take a look at part C though. This is the or, and I really encourage you to always reference that formula. You have access to it on the formula sheet. Instead of using A's and B's though, I'm going to use the variables that we're discussing in this particular problem. It'll make it a little bit easier for us to grab the values we need to grab here. Pierced ears is what I want to say here. All right, so this should be the probability that someone is a male plus the probability that the person chosen just has pierced ears, and then we subtract from that the probability that they would be both a male and have pierced ears. Okay. All right, so the probability that someone is a male. Okay, still, this is out of the 178. We're still choosing from the 178, but look at the total number of males. There are 90 males out of the 178. So the odds of you selecting someone who is a male is 90 out of 178. Okay, now we want to shift to what is the probability that you were to pick someone at random and they had pierced ears. Well, that's actually what we did up here in part A. Okay, again, still out of the 178, but look, we said those who said yes, pierced ears, that's the 103. Okay, and then from that, we are wanting to subtract the probability that someone is both a male and has pierced ears, which is what our answer was here from part B. That was the 19 out of 178. Okay, these all have the same denominator, so we can just go across and do 90 plus 103 minus 19. We get 174 over 178. If you were going to reduce it, that would reduce to 87 out of 89 there. Okay. All right, let's go ahead and flip to the next page here, example number 10. I think you're going to find that there's lots of different strategies you can use for these problems. This one is going to ask us to use a two-way table. Let's read what this problem is about here and see if we can try to do these three parts here. It says a standard deck of playing cards with the jokers removed consists of 52 cards in 4 suits: clubs, diamonds, hearts, and spades. Each suit has 13 cards with denominations ace, 2, 3, all the way up through king. The jack, queen, and king are referred to as face cards. We want to imagine that if we were to shuffle the deck thoroughly and deal 1 card, we are going to define event F as getting a face card and event H as getting a heart card. Okay? And so we're going to make a two-way table because it was quite easy when the information was in a two-way table in this previous example for us to kind of grab the probabilities that we needed from the table. Okay, so we're going to build a two-way table that we're asked to do here in number 1. Okay, so we're just going to simply make 2 rows and 2 columns here. And I'm going to label at the top of each column here, we'll call this event F, and I'll just go ahead and define that represents a face card. Okay, and then I'm going to do the complement to event F, which essentially means it's not a face card. Okay, my other event was H, getting a heart. So I'm going to define this row as being H, which is a heart, and the other row will be the complement to that, which is not a heart. Okay. Now we're going to need to put some totals to our rows and our columns outside of the box here. And so we're going to kind of just see if we can fill in our information. We know it told us here that each suit is 13 cards. So we know if we were to take this whole entire row here and add up just the number of hearts, that it should total a 13. Okay. Now, of those 13 hearts, how many of those hearts are face cards? Well, they told us a face card is a jack, a queen, or a king. So each suit would have 3 face cards. Okay, so if this has to total 13, then that means there are 10 hearts that are considered not a face card. Okay, see how I'm doing that there? Okay, so now let's go ahead and work our way down here. Okay, we know that in terms of how many face cards would there be in an entire deck, well, if there are 3 face cards, a jack, queen, and king for each suit, and there are 4 suits, the total number of face cards in a deck should be 12. So how many face cards are not hearts? That would be 9. 3 for the clubs, 3 for the diamonds, and 3 for the spades. Okay? All right, so as we move across here, we know that this grand total all the way down here should be 52. That's going to represent 52 cards total. Okay, so if I have 9 cards, well, I guess I could fill this row total here. If this is 13, this has to total 52. So this number here must be a 39, so that 13 plus 39 add to be 52. So that means the number of cards that are both not faces and not hearts would be 30. That means all the non-face cards, there are 40 of them, and again, this should total to be the 52 we get there. Okay, so that's number 1. We made a two-way table that displays the sample space. Now that we have this, we should be able to work through and find number 2, the probability of a face card, and I'm going to use this notation, that's the intersection symbol, and a heart card. Okay. Now keep in mind there are 52 cards total, So I want to glance through here and see, okay, where does the face column intersect with the heart column? And I can see there are 3 cards total that are both faces and hearts. Okay, so that's going to be my numerator. Okay, there's the answer for number 2. And then number 3, it says, explain why the probability of a face or heart is not simply the probability of a face plus the probability of a heart. Okay, and then they want us to actually go through and calculate that probability. Okay, so we're going to say the probability of a face or a heart does not equal just the sum of those 2 separate probabilities, because we would be counting the face and heart cards twice. Okay, we would be counting those twice. If you think about this, if we go through here and we say, okay, the probability of a face card is 12 out of 52, and then the probability of a heart card is 13 out of 52, we have accidentally counted these 3 cards here twice. Okay, and so the proper way to do this would be to say, okay, the probability of a face or heart, and again, I'm going to write the formula down. It's really going to help make sure that you get all of the pieces to this formula. Probability of a face card should be 12 out of 52. The heart card should be 13 out of 52. And then we're going to subtract probability of face and heart, which is 3 out of 52, for a grand total of 22 out of 52. Okay? All right, let's